Up until this point, we described a graph at the abstract level as a set of vertices and a set of edges that connects some or all of the vertices to one another. Question, what kind of operations are defined on a graph? We're going to look at graph interface, including a small set of useful graph operations for a directed weighted graph. These operations are the building blocks used by applications that need to answer questions about any given graph. By carefully combining and examining these operations, we can implement the more complex algorithms needed to obtain information from graph data. In the examples on right, these are kind of questions that we ask. Does a path exist between vertex A, D, or any given two vertices? Can we fly from one point to the other? What is the total weight along this path? And how many paths do we have? What is the shortest path of all of these paths? Let's say from Chicago to Dallas. What is the cheapest way to get from one point to the other? If I start at vertex A, where can I go? Right? So there are many connected components, and these are connected components, by the way, by edges. What groups of cities are connected to each other? These are the types of questions that we would like to infer from the graph. And using the graph, we can answer these questions. Let's closely examine some of the fundamental operations that exist in graph. We will use these primitive operations to solve more complex problems that can be represented by graphs. Let's look at this weighted graph interface. This is the interface, or ADT, for a directed and weighted graph. We use vertices with objects of class T to represent the type of storage each vertex has. We'll have two observer methods. One of them is empty, checking to see if this graph is empty or not, and also is full, checking to see if this graph is full or otherwise returning false. Each weight is an integer, and these weights are associated with edges sitting inside this graph. Let's move on to study other parts of this interface. These are the transformer methods. It is important to note that a vertex is represented by an object of class T. This add vertex allows you to add a brand new vertex, assuming that the graph is not full. This means that we have to check to see if is full equals false. And if this is the case, then we can add. There's also transformer for has vertex. This is important because this assumes that a passed-in vertex does not have to be any existing vertex in this graph. At edge. Remember, an edge sits between two vertices. There is from vertex, there's two. So you must have source and destination to define an edge. And because this is a directed, weighted graph, there must be an arrow for this edge. And because this is also a weighted graph, we must assign an integer weight associated with it. So together with the source and destination plus the size of the weight defines an edge. We add it to the graph by way of add edge. This weight is really an assessor method for fetching the weight of an edge as defined from two vertices, the from vertex and two vertex. So once we know the from or the source and the destination or two of an edge that sits in between, we can fetch the weight, which returns an integer. If such edge defined from the from vertex to two vertex does not exist, we return a special null edge value. And this is what we call the sentinel or default value. Or you can think of it as a placeholder that indicates this is a null edge or an edge that does not exist. Back to the color. These are the very four important transformers that we see in a graph ADT. There are several more transformers. Let's look at them next. The very first transformer in this page is get to vertices. Let's say your vertex is here, and along with these vertex, there are four adjacent vertices sitting next to this one. These four adjacent vertices represent four different paths. Path 1, path 2, path 3, path 4. We must store this information inside a data structure, in this case, a queue. which allows for first in, first out. It doesn't matter which direction you start first. Let's say we can start with path 1 by storing, let's say this is node 1 into the queue, and then you move on to the very next one, which is node 2, and then 3 and 4. So in this one example, given the vertex, we have a queue of 4 values sitting inside of it, representing their order of placement as we go through them programmatically. This get2vertices return a queue of the vertices that the vertex is adjacent to. You can also think of it as get vertex adjacent. This queue is also an ADT, which is abstract. And this ADT is an unbounded queued interface. And the reason why we do this is so that any developer can then go into this interface and define any underlying data structures he or she wants to implement this queue. Remember, each vertex is of class T, and this is the generic that we're using for this weighted graph interface to represent the object sitting inside each vertex. If we really think about this, let's say get2vertices does have all of your adjacent vertices sitting inside a queue, then instead of returning this queue interface, we could also have this returned an iterator class. This means whoever calls get2vertices can get back an instance of an iterator that iterates through all of the elements sitting inside this queue. There are many design questions we can think about when we design our interface. This is definitely a very good food for thought. The other 4 methods are really for traversing a graph. Remember what a traversal mechanism is. In a graph, this means visiting every single node, visiting every single vertex inside a graph. So by way of marking them or unmarking the nodes that we visited means we want to use these methods to mark off any vertices that we have already visited so that we don't visit them again. That's what these markers are for. Mark vertex, for example, marks the very vertex that we're sitting on. And this could be done with a Boolean marker. This could be an attribute sitting inside of, for example, T. Is marked is an observer that returns true if the vertex has been visited or marked, otherwise false. Let's say you're done with traversal. You can use clear marks to remove all of the markers or any residual Booleans by resetting the whole graph for a brand new traversal next. This is a very important reset method. This very last method, getUnmarked, returns an unmarked vertex. This ability is useful for beginning a traversal or for continuing a traversal when the application is not sure it has visited every single vertex. We use this getUnmarked to answer questions about shortest path and the number of connected components. We'll study the implementation details for some of these methods described in the next video.